So my name is Danny Caballero. I am a professor in the Department of Physics and Astronomy and in the Department of Computational Math, Science, and Engineering. And I'm going to tell you a little bit about the work that we've been doing over the last few years, borrowing from data science and borrowing machine learning techniques to study STEM education. And like both Corey and Phil said, please feel free to jump in, and Corey will flag me down to have a conversation if you have questions along the way. So before I get started, I want to acknowledge that I am the principal investigator of the group that does this work. So I have the privilege of sharing this work with you. This work is not possible without the folks that you see in this photo and the folks who are named here. They are the experts on these studies. They are the folks that are doing the work. They are the ones who are doing the analysis, doing the theoretical work, and developing these research projects as we go along. And I have the opportunity to share that work with you, being that I'm the faculty member, but it's not my work to own. It's their work, and they are really important. And you'll see them pop up throughout as I present different kinds of work that shows up. So I want to start with this idea of why I focus on STEM education. So STEM education is science, technology, engineering, and mathematics education. I'll use that interchangeably with science education or science and engineering education. I'm a physicist, so why is somebody in physics focused on education research? And I think part of this has to do with the global challenges that we face as a society. So I want to highlight a few of those. So the first is climate change. The planet is warming. There are rising sea levels. There's more extreme weather patterns. There are things that we need to be able to do to address this issue to help folks, particularly those in nations that are close to the coastline, deal with these issues. There's issues of information security, whether that has to do with intellectual property or computer systems, or has to do with election security, things that we need to deal with that help to make sure that those networks and those data are secure. This is associated with climate change, but the current ways in which we run much of our economy focuses on the use of fossil fuels and natural gas production. Those are things that are going to eventually go away, and so addressing these issues with renewable forms of energy and things that are cost effective for folks to be able to power vehicles and machinery and so forth, those things are important. And I think what's most relevant to us now is the issue of disease outbreaks. COVID-19 isn't the only pandemic that the world has experienced. It's certainly not the only epidemic that regions of the world have experienced, and how we address those and how we help folks through these kinds of things are important. Now, I want to also talk about the technological advancements that are important around STEM for a moment, and I'll give you some examples that are kind of relevant to the College of Natural Science. Multi-messenger astronomy is a really critical piece of astrophysics at the moment, where folks are using many different ways of probing the same astrophysical systems to understand them. And the fairly recent detection of gravitational waves by LIGO is sort of a really key part of that. Quantum computing, which is a big piece of work that the College of Natural Sciences is engaged in, shifting from ones and zeros to superpositions of ones and zeros, and really being able to develop more advanced algorithms, more sophisticated calculations, better cryptography, and so forth. All of these things are critical. Bioinformatics, being able to understand the nature of genes and how they may relate to different kinds of experiences that people actually have, right? How we develop therapies, how we develop medications, how we develop ways of addressing persistent disease such as Alzheimer's or Parkinson's and so forth. And extraterrestrial exploration, right? You've probably heard a bit about this lately with the new SpaceX launch and thinking about us getting to Mars and so forth, right? A lot of these kinds of advancements that are needed to get us there and to help us establish an understanding of just our neighborhood is really important. And I see my role not necessarily as addressing these issues or investigating these particular advancements, but rather enabling people to do that work. I think for me, there's a greater impact in enabling other people to do these kinds of things than for me to do it by myself. And so I'm going to make a pretty bold statement, but I don't think there's any solutions to these global challenges or advances to these critical technologies without high quality STEM education. It's just not possible to prepare folks to engage with these kinds of things without the highest quality STEM education that we can engage in. And so shifting to talking about STEM education, it's something that's shown up a lot, and it's shown up a lot in national documents. I think one of the more recent ones is Rising Above the Gathering Storm, which was a document from the National Academy of Sciences talking about how to energize and employ America for a brighter economic future. It sort of highlights STEM education as one of the pathways. Rising Above the Gathering Storm 2, if you will, rapidly approaching Category 5. People really liked hurricane analogies at this time for some reason. I'm not sure why. During the Obama administration, there was the report to the president that was called Engage to Excel, or the so-called PCAST report, which talked a lot about investments needed in STEM programs and STEM teachers. And most recently, the Committee on STEM Education has developed a document called Charting a Course for Success. And I want to draw from that particular document because I think it summarizes very cleanly 3 critical aspects that we need to address. The first is building strong foundations in STEM literacy. This is not just K-12, but also in higher education. We need to work on increasing diversity, equity, and inclusion in STEM. These are who gets to participate in STEM education and in STEM jobs. Typically, those folks that have filled those jobs are male and are predominantly white folks. Preparing the STEM workforce for the future. I sort of addressed some major global challenges that we have and some technological advances that we're trying to engage in, and thinking about how we construct our STEM preparation to address those issues is critical. So for higher education STEM, we really need to continually investigate the learning outcomes we have in our courses and in our curricula, and iteratively improve our instruction as we go along. We need to address the culture of STEM to increase recruitment and to better support retention, particularly for women and folks of color. I'll identify some metrics here in a moment. And we need to think about modernizing our curriculum and pedagogy to address these global challenges, thinking more about what world our students are going to be moving into, rather than where they are at the moment. So I want to highlight Michigan for a moment, because I think one of the things that's really wonderful about working at Michigan State University is that it is a land-grant institution. It is, the economic powerhouse for the state. It prepares many students to continue to work in our state. But I want to talk a little bit about what STEM looks like in Michigan at the moment. Many students in Michigan don't achieve proficiency in math and science. About 50% of 4th graders and 50% of 8th graders are earning proficient scores on their math and science assessments at the moment. Students of color and those who are economically disadvantaged, they're disproportionately affected. Those students testing proficient from those groups varies between about 8% and 20%. Advanced STEM courses are not really accessible to many students in Michigan. Physics isn't offered at 20% of high schools. Calculus isn't offered at about 35% of high schools. And students students who are of color are disproportionately affected. Only about 25 and 50% of schools offer these advanced courses in those schools. Few high school graduates demonstrate readiness for college. Only about 37% of students statewide earn scores on the SAT mathematics test that is considered to be college ready. And if you look at economically disadvantaged groups of students, it's more like 18%. Few students who enroll in two-year colleges complete degree programs. In Michigan, we have a lot of two-year colleges, but only about 13% of students complete their degree program. Nationally, that percentage is closer to 28. And few women and few students of color earn STEM degrees. If we look at Michigan, only about 23% of computing degrees are awarded to women, only about 14% are awarded to students of color. And this is particularly important for Michigan State University because more than 75% of students at MSU are Michiganders. So we have a societal, and I would argue a moral obligation to address these issues in any way that we can at MSU. And the way that I go about it is through research. So I'll tell you a little bit about STEM education research briefly. STEM education research is studied by STEM professionals, people who are physicists, chemists, biologists, mathematicians, etc., by training, who want to understand how students understand STEM concepts, STEM practice, how students develop an affinity for the discipline. They study curriculum and pedagogy, how those affect student outcomes, how those affect student participation, how those affect degree earning. They study tools, things like laboratory equipment, things like computer models, and how students work with and learn from those. And they study different contexts, different ways in which students might participate in programs and so forth. And these are typically done within a given discipline. So for example, Phil mentioned that I'm in physics, and so I would do physics education research. Recently, I've been appointed to computational math, science, and engineering, so we're beginning to develop computational science education research. But at MSU, we have chemistry education, we have biology education, mathematics education research, etc. And all of our fields have theoretical components, experimental components, and applied research. The work I'm going to show you and the work that I'm most comfortable doing is work that's applied because it has some sort of potential outcome for students, but it does draw on theory. My sort of group within our group is called the Learning Machines Lab. And we focus on generating quantitative evidence for understanding issues of STEM education. This is sort of in contrast to qualitative research, which is very rigorous and requires many years of work, but it focuses instead on individual students or groups of students and develops really deep narratives of how they experience or how they engage with STEM classes, experiences, etc. We're working on generating quantitative evidence. For me, this started with a piece of work that my future PhD student, John Aiken, and I would do several years ago. So we looked at the physics major and we said, hey, there's a lot of students that declare that they want to be a physics major, but how many of them actually become physics majors? And where do they start and where do they end up? So this graph is called a Sankey diagram, and it basically illustrates the first major that a student declared and the degree program that they ended up earning their bachelor's degree in. And what you can see from the diagram is that maybe about 60% of students who first declare a physics degree actually earn that degree. But students who earn a physics degree actually come from a lot of different places. They may have been engineers initially, they may have been other STEM majors, they may have been non-STEM majors. And students who declare physics initially also go out into other programs. They become engineers, they become other STEM majors, they go into non-STEM programs. And so there's a lot of opportunity here to understand the nature of these transitions, the ways in which students go through this program, not just in physics, but in STEM more broadly. And this has been a kind of a driving piece of work for us throughout the development of this group and throughout the development of our research program. And because this data is so complicated and layered, we began to investigate ideas of machine learning to understand these things. And so when I say machine learning, you know, maybe you think of something like this, right? This is a very, when you Google machine learning, this might be the first image that comes up, where you have a human and a machine, and they're somewhat hybridized in some sort of strange T-1000 Terminator 2 kind of situation. But if you dig a little further, you find sort of more humorous takes on machine learning, right? So this is from the XKCD comic series that basically talks about machine learning as this kind of black box where you stir your data around and you get the answers that you're looking for if you stir enough. And it's interesting because there's a lot of different ways to go about machine learning. And as our group has learned more about it, there's a lot of different ways of thinking about why you would engage in machine learning and what you care about when you do it. For example, if you're on the Amazon website and you're getting suggestions for things that you might be interested in purchasing, there's machine learning doing that work. But the stakes are very, very low, right? It's not a big deal if Amazon accidentally suggests to you the wrong set of headphones or the wrong hairbrush. But there's some major implications if predictions for students or classrooms are done poorly, or if we're not able to interpret the underlying models appropriately. And so we have to really think about unpacking the black box and what we're trying to do in our work to understand all the way along what our predictions are suggesting. So I'm going to give you a sense of machine learning sort of in a set of layers, if you will. So starting with sort of, is this machine learning, right? The idea of starting with data and putting it into a machine and getting results, right? That's often the way that folks think about machine learning, as this black box that produces results. And if it did that and we were able to sort of produce publications around that, we would certainly publish a lot of papers, right? But it's a bit more nuanced than that. One of the things that we really spend a lot of time on is thinking about how we construct our models from these data. And so we use an approach where we split our data into a training set and a test set, meaning a set that we're going to develop our model with, and then a set that we're going to compare the predictions from our model against. So we take that training data and we feed it into a model, something like linear regression or a random forest regressor, where we're trying to predict some sort of outcome. And we obtain fit parameters, namely the numerical predictions associated with the model that allow us to decide how well we are predicting a particular outcome. Then we use those fit parameters to predict the output from that test data. So we take that test data and we predict the output. We already know what the test data says about the output, but we're using the model to then predict the outcomes. And then we evaluate the model. So we look at that output and we compare it to what the actual output is from the test data. And by doing that, we can say something about how well the model is fitting, what kinds of data it's fitting in what ways, and whether we're over-predicting or under-predicting in certain ways, and so forth. Now, that's quite simplified, and you're going to see my cat, who's going to be my parrot for a moment. Sorry about that. We do that once, we do it again, we do it again, we do it 100 or 1,000 more times. And by doing that, we build confidence in the model. And a lot of the approaches that we use take into account many, many different iterations of our modeling process. So just to give you a sense of the landscape of what we do two forms of machine learning. The first is supervised learning. This is the kind of learning where you actually know the outcome. For example, you're trying to understand why students earn a certain grade in a course, and you know their prior preparation, you know their attendance records, you know maybe their gender, things like that, and you're trying to predict what they're going to do in that course in terms of their grade. There's two approaches to that we use. One is called classification, where we're really just trying to separate, we're really just trying to separate the two, maybe two sort of outputs, high grades and low grades. And the other one is regression, where we're actually trying to predict the grade itself. And those two approaches we use kind of commonly when we're doing these kinds of studies where we know what the output is and we can compare it. The other approach we use is what's called unsupervised learning, where we actually don't know what the outcome is. And a common technique for us is called clustering, where we have some set of data and we want to know how they're organized together in some way and how we might interpret that. So we might build some sort of clusters that interconnect different bits of data. So maybe you're looking for groups of students or groups of outcomes, but you don't know ahead of time what they are. The last one is dimensional reduction. This is common when you have hundreds or thousands or hundreds of thousands of dimensions to your data and you want to sort of find the sort of key elements associated with your data. We don't use this as often because our data isn't really that high dimensional, at least at the moment, but it is common to see. So as education researchers, we use machine learning for a variety of reasons. First, the data that we have access to is increasingly complex. It's large and it's fundamentally relational. If we start looking at data from the registrar, this is stored in databases that are related to a variety of different information we have on students. It's complicated because students add and drop courses. They go through the degree programs in very different ways. And it's large. We have a lot of students at MSU, and we have a lot of them going through programs. The models that we have from data science, they're able to handle a wider variety of these data. A lot of the traditional models that we use in STEM education are hinged upon having what's called continuous data, data that spans the number line, if you will. And a lot of the predictions we use often are also spanning that number line. When you have those kinds of data, traditional approaches to modeling that data can be quite useful, but oftentimes the questions that we're interested in have data that violate assumptions of those models. The frameworks that we use to construct and develop these models are really robust. I showed you this diagram of how we go about splitting our data and making predictions and testing it. Those frameworks are robust, and the ways in which we evaluate them are well documented. We can sort of say a lot about what our models are doing. And because we have this data that we have access to that's new, we have these new approaches to doing the modeling, we can actually ask and answer really new research questions. We can ask questions about data that is much bigger than we had in the past. We can ask questions about data that's much more nuanced than it was in the past. And for the students that are working in the lab, the undergraduates, the graduate students, the postdocs, who are not students but researchers, I think we're better preparing them for 21st century careers. It's not necessarily the case that undergraduate students or graduate students that work in the lab are going to be education researchers. They may go do other things. And by having them engage with machine learning and data science, they are better prepared for a wider variety of careers that they might find interesting. It's important for us to think about that as well as we're, sort of training people in our field. A couple of caveats, though. Machine learning isn't always the right tool for the job. As I tell my students, and they tell me, we want to start with simple, and we want to then try to add complexity to it if we need to. And interpreting the results from machine learning models can be quite a challenge. They have some pretty complicated and sophisticated mathematics that underlie them. And so that can make it difficult to understand and interpret the results, which is for us really important. Again, going back to the Amazon example, it's not a big deal if Amazon suggests to you the wrong set of headphones. It's pretty problematic if we suggest something to a student based on a badly interpreted model. So what I'm going to do now is walk you through 3 examples using the classification, regression, and clustering themes as ways of understanding the research that we do. And then we'll talk a little bit about some of the wider examples that we have. So again, I'll start with classification. This is the idea that we can build a model to predict, 1 or 2 or more outcomes, basically high, low grade, for example, pass, fail in a course, being admitted or not into a program. Those are the kinds of questions that we ask. My PhD student, Nick Young, has been working on a project that is at the intersection of machine learning and diversity, equity, and inclusion. And he's very interested in how we address issues of diversity with regard to graduate programs, particularly in physics. And so if we look at a PhD applicant who's admitted to the program, we might have a decision tree to decide whether that student is accepted or not into the program. So for example, if their GPA is below 3.0, we wouldn't admit them. If their GRE score is below 150, we might not admit them. If they have research experience, they have a high GPA and they have a high GRE score, maybe we're likely to accept them. And so this approach uses a decision tree to distinguish the different things that people might be using to determine whether a student is admitted to a program or not. What Nick has done is he's developed an approach that uses a technique called random forest, which is a lot of different decision trees, to determine which of these factors are the most important in terms of predicting whether a student is admitted to a program. The way he evaluates that is called an ROC curve. Now, I don't expect you to understand all the details of this, but really what tells us if his model is a good model, at least to begin with, is the blue space that's taken up in this diagram. So the more of that blue space that's taken up, the more likely that Nick's model is able to predict a student being admitted to the PhD program, the more confidence we have in the features that are being used. And the way that we test that is by building a model and then removing features and replacing them. So for example, if Nick were to remove a feature that was important, you would see that curve shift down towards the line that goes diagonally through it. The closer we get to that diagonal line, the worse our predictions are. So we would put that back and we'd really try to build a model that's more predictive, pushing the curve closer and closer to that corner. So through this approach, Nick has been able to produce a model that demonstrates a variety of features that are important for predicting whether a student is admitted to a PhD program in physics. And the top two predictors are the student's GRE score in physics, that is the exam that they take that is meant to demonstrate some understanding of canonical physics content, and the undergraduate GPA from the program that they graduated from before they were applying to the physics program. And as you can see, there's a number of other features, other GRE scores, the selectivity of the institution, the type of program that they're in, et cetera. But what's interesting from Nick's results is that he can predict admission with 75% accuracy by considering only the undergraduate GPA and the physics GRE score. That is, these two numerical metrics can essentially determine whether a student is going to be admitted with 75% accuracy. Now, the diagrams that I'm showing you here are basically taking the subspace of GRE score and undergraduate GPA and showing you students who were admitted and students who were not admitted to the program. And you can see in the right diagram, the sort of red and gray lines that illustrate a boundary, basically, of where you're more likely to be admitted to the program, which is, effectively a high GRE score, and even having a sort of moderate GPA. Now, the issue associated with this is really that in the literature, that metric-heavy admissions like this limit the participation of women and folks of color in graduate physics programs. And so if we're making decisions primarily and maybe even implicitly on undergraduate GPA and physics GRE scores, we are not really considering the issues of diversity in advanced physics study in ways that we probably should. Nick is doing more of this research with additional schools and digging into more details here. But I can tell you that much of the work that we find is that this is somewhat reproducible across a number of contexts. Now, that's a classification problem. So we'll shift gears and we'll talk a little bit about a regression problem. This is similar in the sense that you have a bunch of input features like Nick has in his research, but instead you're trying to predict a number on a number line. So something like a grade, for example. Now, what we see, our context for when this is very useful, is considering what we call active learning classrooms. So what we find in lots and lots of research is that students who complete active learning courses tend to learn concepts, physics, chemistry, biology, doesn't matter which course really, they learn them more deeply. The picture I'm showing you here on the left are pictures of my colleague Vashti Sautel's Introductory Physics for the Life Science class, where students are building experiments and models and really deeply trying to understand the underlying physics concepts in the course. Now, a very old piece of data that shows up is from Richard Hake in 1998, where he studied a variety of courses and showed that students who were taught in a traditional manner tended to perform less well on an assessment of their conceptual learning than students who took an active learning course. The way that Hake tells it is students who are in traditionally taught courses tend to learn about 25% of the concepts that they didn't already know, and students in active learning courses tend to learn about 50 to 60% of the concepts they didn't already know. And so a big question in the field, even though this has been reproduced many, many times, including at MSU, is why? Why is that the case? So my PhD student at the University of Oslo, John Aiken, has been interested in studying this and has begun a project where he looks at how the particular school, the kind of course that a student is taking, and their prior preparation might predict their performance on those kinds of assessments. What John did was kind of unique in that he started with simulated data. So what he did was he prepared a data set looking at student scores on these assessments before and after hypothetical instruction. And so what you see here is a distribution of courses that would be considered traditional, meaning lecture-based courses, and courses that are more transformed in the sense of having more active learning in them. And the simulated outcome of those data showing that students in the transformed course perform a bit better than students in the traditional course. The way that John constructed this data set was to bake in prior preparation as being the largest effect, the course that the students took, whether it's transformed or traditional, being the next largest effect, and the school that the students took the instruction at being the smallest effect. And what he wanted to see was, if I use different models, how well do my models perform in predicting this output? Because if we don't have good models to understand these data, we may make conclusions that don't make a lot of sense. So John used three techniques: a basic linear model, which is the blue line, a hierarchical linear model, which basically takes into account the nested layers of being at a particular school, taking a particular course, taking a particular approach, and then XGBoost, which is a common machine learning technique for predicting numerical outcomes. And what he finds is that all of the models were able to show that prior preparation has the largest effect, the course has the next largest effect, and the school has the smallest effect. But if you look at the diagram, the gray and the red lines overlap pretty well, showing that XGBoost is doing a really good job of predicting the post-test scores as compared to the linear models, which seem to have taken into account the three peaks that you see in the pretest score a bit more. So what John suggested from his simulated data was, well, maybe XGBoost, this particular technique, is doing a better job at making these predictions, and so maybe we should trust its results better. So John then looked at real data. So this is coming from a colleague of ours who has data on about 8,000 students that take these introductory physics assessments. And you see some pre-test scores and some post-test scores. And John took the same approach, modeling that data, and found that, well, in fact, you know, XGBoost does a pretty good job. I mean, at least compared to the linear models. But in fact, the linear models still do okay. They don't do nearly as bad as when the data have these three peaks in them. But you can tell that the ordinary least squares fit is not really good. The regular linear model is not really that good. But what he concludes from this is that we have to use a lot of different models to evaluate our data because there may be a multiplicity of good models. The XGBoost and the mixed effects model are both pretty good, but all of the models actually suggest that prior preparation is the dominant predictor. And so with this sort of consistent message of, well, prior preparation is really important, what are the next level effects? And that's where you get some mixed results that we're still working on investigating. All right, the last example I have for you is from clustering. This is from my own work as a PhD student, where at the school that I was at, we taught students to do computational modeling using a computer to make models of physical systems. This is a Python program that students would have seen in that course, where they are looking at how a satellite goes around the Earth, and they have to write the program statements to make the satellite go around the Earth in a geosynchronous orbit. And so after they work with their lab mates, they will have constructed a program where they have made edits to the green lines and they have added the purple lines to build a model that follows the satellite as it goes around the Earth. Now, students in this class would have had this kind of experience every week for 13 or 14 weeks, so they would have constructed many, many kinds of programs. And what we were curious about was, well, can they construct these programs on their own? And if so, what kinds of challenges do they face when they do it? So this was a big introductory course that had about 1,300 students taking it. And we gave them a program that they had to do exactly the same activity: write the initial conditions, calculate the force, implement Newton's second law, but they had to do it by themselves. And what we found was that about 60% of students could do so with no problem at all. But about 40% of students generated one or more errors in their code when they constructed it. Now, we were interested in the students who had these one or more errors because we wanted to know, well, what kinds of errors do they have? What does this tell us about what changes we need to make here to our instruction to help them be more successful at this? And it turns out when you go through and you look at 1,300 pieces of code, there's precisely 117 different ways that it can go wrong, it seems like. So that's a lot of different ways. And we were really unclear on how to address each of these issues. So by using cluster analysis, we were able to find commonality among these 117 different approaches that students took. That's what you see in the sort of colored bars there. This is a so-called dendrogram plot, which talks about the closeness of the different errors that students would make in their code. And so the colored bars represent the different clusters that we looked at closely. So within those bars are 1,300 students, but there's only about 5 clusters that contain about 80% of our students in the data set. And so what we found was that in those 5 clusters, we could identify the sort of major error that showed up in the student's code. So the dominant one would be that they'd have a sign error in their force calculation. They would make the force repulsive instead of attractive, for example. About 20% of students had perfectly running code, but they made an error in their initial conditions where they transcribed 2 numbers incorrectly, which leads to output that is incorrect. The next 2 actually involve students not necessarily understanding the relationship between vectors and scalars by treating the net force, which is a vector quantity, as a scalar, or raising the vector to a power, which is a mathematically inappropriate operation, and so forth. And in this paper, we identified things that we might be able to do to address these issues, to sort of give students more opportunity to engage with making sense of the direction of the force and how to address vector issues in the classroom. So that's a clustering example. Now, for the last couple minutes, what I want to do is just show you a smattering of the things that other folks are working on in the group, but not go into nearly as much detail. So Joe Wilson, who's a student that I help advise at the University of Colorado Boulder, is using a technique called natural language processing to understand how to classify students' statements on an assessment. So students are typing out their answers to questions, and Joe's code reads in that language and tries to categorize it into multiple different categories to more quickly assess student thinking than we have been able to do in the past. We had to do all this by hand, which takes weeks to do, and Joe's code can do it in a few hours. Jen, who's a student that I've worked with at Beijing Normal University, has been looking at course taking patterns. There's some suggestion that students taking courses in cohorts is productive for them in the sense that they are more likely to complete their degree program. And Jen has been looking at informal social networks that show up in MSU course taking patterns, and has found that students who tend to stay in the degree program tend to have more strong connections between them and other students who are taking courses, which leads to a suggestion that maybe having cohorts of students take courses is a productive way of dealing with retention. Matt Ring, who just graduated from MSU with his physics degree, has been looking at large curricular impacts, namely in chemistry, and how those affect persistence in degree programs. So we made a big change to the way that we teach chemistry. And so we have data from before and data from after. And Matt's been looking at whether there are additional effects associated with that curricular change in terms of persistence and in terms of earning grades in follow-on courses. Like I said, he just graduated, and actually Matt is now a master's student in public policy and data science at George Washington University. So, this can lead to really interesting outcomes for students. Nils is a student that I supervise at the University of Oslo with Nick Young, and he's been digging in more into the GRE and looking at how students' prior preparation influence their GRE scores. What he's found recently is that, the majority of the prediction can be accounted for in terms of an undergraduate GPA, the gender of the student, and how big their the program is, how big their physics program actually is. Students at larger schools, students who are male, and students who are in higher undergraduate GPAs tend to have higher GRE scores. John, just to show him again, has been looking at the factors that predict students earning physics degrees. And what he's shown is that it's really important for us to engage with students in the first 2 years, because if a student takes the modern physics course, they are very, very likely to earn a physics degree rather than to switch to another degree program. And finally, Alyssa Watterson, who's my PhD student here at MSU, has become very interested in how all this work relates to transfer students. What she's begun is to look at
Phil, did we lose Danny? It looks like he got disconnected.
Yeah, I think we did.
So, Phil, one of the questions I was going to ask Danny, and maybe as we wait for him to sign on, you can answer just because your experience in your previous role as physics chair is, we talked about the active learning classroom, and I appreciate him showing pictures of that because it really gave us an idea of what that looks like. Is the trend for classrooms to be kind of going that way, or do you think that most departments are still stuck with this traditional classroom style class?
Yeah, I think the first thing to note is the thing that's called the new classrooms has actually been used for a long, long time. And if you have a small lecture with 10 to say 40 or 50 people in it, you can do very individualized interactions and get people to respond. The classrooms that don't work very well are the ones with a large number of students, 300 students, say. And what we're trying to do is make them more personalized. And the way to do that is engage the students, and you can call that active learning. The new things that are happening now is that the active learning has a different format, and we're trying to head in that direction. It's actually more expensive to do so. And the new STEM building is designed particularly for that, for active learning and engaging students in physics, chemistry, and biological sciences. So we're part the way there to getting all of these introductory courses to be active learning environments, but there's still a long way to go.
Great. So I don't see Danny signing back on, but Phil, anything else you want to add? I'm putting you on the spot, but anything else you want to add to Danny's presentation, or additional comments you want to make in regards to STEM education happening within the college or the university?
Yeah, there's a couple of things. The first thing is that what Danny's doing is very new. We haven't had people engage in this approach to trying to figure out what's important in STEM education. And so he's at the forefront, and he's engaged with people at the University of Oslo. And the reason he's working there is they're doing a complete transformation of their introductory curriculum across the university to include computational methods. They see computational methods as being vital to the future of all of their students. And so they're engaging with that. In terms of what's happening here, engaging with schools at the moment is a major issue. And there are several efforts on campus, including one in the College of Natural Science, which is working towards better online tools. And the online tools are supposed to improve our online delivery. And those tools are applicable to schools. So we're trying to do both on-campus and off-campus efforts in that area.
Great, thank you. And I'm obviously disappointed we don't see the rest of Danny's presentation. Oh, you know what? I think he's signing back on right now. Let's see if he reconnects. Phil did a great job covering for you while you were gone.
Thank you. Yeah, my internet just completely went out at my house, like all of a sudden. on the last slide, and so I'm on my phone. I don't know how it happened, but I saw it happening as I was finishing. So
It only happens during the important times, right?
it's literally never happened the entire summer. So anyway, thank you all. And I will be happy to take your questions. I'm so sorry.
I asked Phil a question about, I was saying how I appreciated you showing the picture of the active learning classroom because it gave us a visual of what that looks like. And I asked Phil, and he already answered, but if that was kind of the trend happening across campus in all disciplines or just in physics and NatSci.
Yeah. Yeah, it's definitely happening as a trend, I think, across a lot of the programs.
So I am going to put you on the spot for a little bit because I want to ask you about, last time I spoke with you, you were also doing some work in Ghana and West Africa. Is that still happening? And do you want to tell everybody about that project?
Yeah, sure. So that program was spearheaded by physics students who wanted to try to help physics education in Ghana in some way. And, they initially started with not necessarily understanding what the nature of things were and what the project would be and so forth. But over the last year or so, they developed a really deep understanding of what would like an actual partnership with Ghana look like, and how would that actually work. And so those students have graduated. We had intended to recruit additional students, which we started to, and then with the COVID situation, we haven't been able to continue much of that work. At the moment, we're collecting textbooks for Ghanaian teachers, because that's one of the major resources that they are lacking in their schools. But we do hope to go back and have Ghanaian teachers come visit and sort of begin to share ideas about teaching and learning in physics through that program.
And those were undergraduate students, right? So
those are all undergraduate students. Yeah. That's right.
That's pretty remarkable. So I'm going to wait a couple seconds here and see if anybody has any additional questions, but I think we might. There was one question that came in, but I think it's more of a connection question at the end. But Danny, thank you so much for participating and doing this for us today. We really appreciated it.
No problem.
Okay, so I want to remind everybody that on August 26th at 1 p.m. we are going to be doing a back to school town hall. So Phil will be presenting along with some of our associate deans, our director of undergraduate studies, and our curriculum developer to really share all things back to school and answering any questions you have in regards to student support, faculty support, what the experience is going to look like. And we really encourage all of you to attend. Just like our past events, you will get a follow-up email tomorrow that will include the link to this event. And it will include the information and registration link for our town hall talk on the 26th. We do encourage you to send in questions ahead of time, but if not, there is always the opportunity to ask questions live. And you know what, Danny, I'm gonna unmute you here. I do see that we had one question come in, and let me see if I can. We had a question come in that says, with COVID-19 forcing changes in college learning, is it time to start talking more generally about transformation to college learning?
Transformation to college learning. In terms of like remote learning, I guess, is that, I'm not.
I'm assuming, yes, remote learning, online learning.
Yeah. I mean, I think, yeah, it's a really good question. Consider how we do what is effectively distance learning and how we do it well. I do think there's a lot of value for students to be in person and work with stuff and work with groups. Excuse me, but trying to figure out how to do the best distance learning courses we can in situations where we have to do them. And in other situations, trying to figure out hybridized courses. I guess my personal hope is that we get through this and we can go back to being in person.
Okay, I think we're still having a little bit of technology issues, but we will make sure Ethel, get you the answer to that question. So I think this is probably our cue that we are time to finish. We hope to see everybody on August 26th for our next event. And thank you, Danny, and thank you, Phil, and everybody for being here today. Bye-bye.